workshop. We have Alex Lubotzky from here, and he will speak about, can you hear the shape of a Cayley graph? We don't have a Cayley graph, so we can actually experimentally check this.
Thank you very much. Being the last speaker, it's my duty and pleasure to thank the organizer for putting up such a nice conference. I'm grateful to you, though I have the feeling that various people whom I promised various things and I postponed it because of that conference are less grateful. Anyway, thank you very much for the efforts. What I'd like to talk today is something which kind of started with a famous, very, very famous paper by Mark Katz, Can You Hear the Shape of a Drum? And which is basically a very beautiful title for a very simple and natural question. Can you recognize, I think he originally talked about a domain, can you recognize a domain in the plane by knowing the spectrum of the Laplacian acting on functions on that domain with various boundary conditions or whatever, and you can easily generalize it, and I think this is the way it was considered in much of the literature. You have a manifold, a closed manifold or not closed, in various contexts, to what extent the spectrum of the Laplacian determine the structure of the object. Now, working in this conference in discrete object, we of course can ask the same question, and not just we, this has been asked. Can you recognize a graph from the eigenvalues of its Laplacian or its adjacency matrix? Now you can ask it for finite graph, you can ask it for infinite graphs, and and the answer is no. More or less in most general context. It took, by the way, like, I don't know, maybe 40 years till the original problem of Mark Katz got the negative solution. There have been various negative solutions for various manifolds, but I think the exact original question was solved only 40 years after that. And some of the, and many mathematicians contributed in one way or another. So I'm not an expert, and I definitely won't give you a general survey, but I want to concentrate on a little aspect of it, which is first of all about finite graphs. I will go back to manifold, and mainly about Cayley graph. So somehow, the most elementary and beautiful construction of graphs, or of a method of graph, which are isospectral and not isomorphic, is due to Sunada, and it's so elementary and so beautiful that let me write it on the blackboard. Well, I should say, there have been before, there are various graphs, like strongly regular graph, which they have only few parameters, and these parameters completely determine the spectrum. So you can arrange a strongly regular graph to be isospectral. What I'm really interested today is to get graphs of bounded degree, to get infinite families of bounded degree, which are isospectral, namely the same spectrum, and not isomorphic. And by the way, the question as to these two parts, and they are sometimes the second one is more difficult than the first one. You prove that something is isospectral, but maybe they are isomorphic. Let me instead of talking up in there, let me show you the method of Sunada as for graph, but this will be Schreier graph. So here is a definition. Two subgroups, if say H1 and H2, inside the group G, let's say that G now is a finite group, are almost conjugate if for every conjugacy class C in G, H1 intersection with C, the size of it is the same as the size of H2 intersection with C. Then, of course, if H1 and H2 are truly conjugate to each other, then they are clearly almost conjugate. But this can happen in other cases. Let me give you my favorite example. Look at H1 to be Z over PZ cube. Take P to say to be a prime number, and take the vector space of dimension 3, the elementary abelian group of order P cube, and take H2 to be the upper unipotent group. This group, all these matrices were this in Fp, in the finite field of order P. So this, now both groups are of order P cubed. Both groups have the property that every element of them is of order P. Let's say that P is more than 3, or I think 3 is still okay, maybe more than 3, I don't know. Okay? So we have now two groups with this property, but one is commutative and one is not commutative. Now we can embed both of them by Cayley theorem into the symmetric group of they both act on themselves. So we have an embedding of both of them into the symmetric group of order P cube, right? And then now I claim that they are almost conjugate. They are clearly not conjugate, because if they are conjugate, they should be isomorphic to each other. One is abelian. Why they are almost conjugate? Because every non-trivial element of HI acts on itself by left translation as an element of order P without any fixed point, which means that if you think of it as a permutation on the set of P cube element, this is a permutation with P square cycles of length P. And therefore, they are all conjugate to each other within this group. So all the elements here, the non-trivial, are conjugate to all the elements here. In particular, they are almost conjugate. Now, the theorem of Sunada, which is really so trivial that it's really a proposition, says that if H1 and H2 in G are almost conjugate, and S inside G a set of generators, then the Schreier graph of G mod H1 with respect to S is isospectral. So how should I write it? I don't know. Isospectral, namely the same spectrum as the Schreier graph of G mod H2 with respect to the same S. And it doesn't matter what is S, doesn't matter what's the size of S, what is it? The proof, you want to say something, Benji?
Yeah, Mackey used exactly this phenomenon to show that the non-commutative group measure preserving isomorphism and unitary isomorphism are not the same already for finite.
Okay, good. I didn't know this history.
In fact, algebraic number theory in the
Right. This was used to give, it's a very old phenomenon, used to give a number field which with the same zeta functions, etc., etc.
but unitary but not pointwise.
Right. So in fact, what you really prove here,
I missed the argument for why they're almost conjugate.
okay, because take every non-trivial element in HI. This is an element of order P, acting on the group by left translation. So it has no fixed point, which means that as a permutation on itself is a product of cycles of length P, of P cube and p square. And this is true for all the elements here. So all the elements here are conjugate to all the elements here. In particular, there's only one conjugate, except for the trivial element, one conjugacy class which they intersect and all of them. Now this is in fact happens, and actually this is really if and only if, we as G representation, L2 of G mod H1 is isomorphic as a G representation to L2 of G mod H2. And that's basically equivalent. Now the proof of that, I won't give it, but it's a real exercise. The point is that graphs, the eigenvalue, like the adjacency matrix of a graph is diagonalizable. The eigenvalues are completely determined by the traces of the powers of the adjacency matrix. Now if you go to these traces and you see how many traces really means how many closed paths you have, you see that that's exactly, but I leave you this as an exercise. But it's really exercise. Now he got a big theorem out of it, which with another half a page, because he proved that there exists Riemann surfaces which are isospectral and not isomorphic. So this was basically this proposition plus a very clever use of some facts. One of them is deep by Margulis and one is classical to get surfaces. I wish I would, maybe I don't know, should I say that? Maybe I'll say the proof for those who are that. He says, take such an example and take the Teichmuller space of all the Riemann surfaces of genus G. There are many of them, and they are in one-to-one correspondence with conjugacy classes of the surface groups pi G as a lattice in SL2R. According to some classical results, I'm not sure, maybe go to Leon Greenberg, most of them are maximal subgroups. Take such a group and map it onto such G. And then pull back the H1 and H2. So these give you two Riemann surfaces. Now, if these two representations are the same, when you induce it up all the way to SL2R, they are the same. This proves they are isospectral. Why they are not isomorphic? Well, do it with non-arithmetic lattices. According to Margulis' theorem, if you take a non-arithmetic lattice which is maximal, then it's equal to its commensurability group. And therefore, the two subgroups cannot be conjugate. Anyway, you have to know a little bit, but this could be a one-page paper, except of the fact that the annals probably felt bad to publish a paper which would be one page. So somehow he said more, over 10 pages. But basically, this is an argument of one page if you know enough background. Anyway, but let me challenge you now to show you that in general, this is a difficult problem. So take this example now. We know by this Sunada proposition that these two graphs for every set S are isospectral. But why they are not isomorphic? To be honest, I don't know. I don't know. I don't have any machinery to say non-isomorphism. Now, isomorphism of graph, as we all know, okay, now Baba had his fancy work, which he managed to get the algorithm to be much better than what was known before, but still, to prove the two graphs are not isomorphic, it's a highly non-trivial issue. It looks clear that that there exists some S for which they are not isomorphic. How can they be all isomorphic? But I don't know to prove that. Anyway, this method, first of all, gives you the Schreier graph. Schreier graphs are very much non-homogeneous, non-transitive, right? The group does not, if you have a Cayley graph, then you have Cayley graph from the right, then you act from the left and you get transitive graph. Schreier graphs are usually very not non-transitive. And moreover, even if you got the way, even if you got the way I explain now how to get from this proposition Riemann surfaces which are not, which are isospectral and not isomorphic. That's, as I said, this is possible to prove over there. They are not isomorphic, but by the way of construction, they are the so-called commensurable. Namely, they have a finite sheeted cover which cover both of them. So they're not isomorphic, but they are at least cousins. Not identical, but very close to each other. Here is another open problem, quite famous open problem. Is it possible, are there closed Riemann surfaces of genus G? They must be of the same genus. That's not difficult to prove. Which are isospectral and not commensurable. Not just not isomorphic, but not commensurable. That they are not commensurable to each other. Namely, they don't have a common finite sheeted cover. This is a famous open problem. Alan Reed proved the following results. Assume you have two arithmetic Riemann surfaces. Whatever it means, I will touch a little bit in a second the meaning of arithmeticity. If you assume you have two arithmetic Riemann surfaces which are isospectral to each other, then they are commensurable. So for arithmetic, isospectrality does not imply isomorphism. That can be proved. There are examples that need a little bit more argument, but they are at least commensurable. So in some sense, the Sunada is the typical example. In fact, the type of work I'm going to present here, which is a joint work with Uzi Vishna from Bar Ilan and with the late Beth Samuels, started with the idea to show that Reed theorem is not true if you go to higher dimensions. That even for arithmetic manifold, you can find arithmetic manifold which are isospectral and not commensurable. But along the way, we could kind of as a shoot-off, we got also a Cayley graph. But before going to that, let me say what we want. Let me say something about Cayley graphs. There's very little, surprisingly, there is very little literature about isospectrality of Cayley graph. Babai in the 70s got interested in this type of questions, and he wrote that if D equal dp, this is the diedral group. The diedral group of order 2p. P is a prime. You take the diedral group of order 2p. This is just a semi-direct product of the cyclic group of order p with the involution acting on it. The diedral group of order p, D is at least p over 64 pairs of generators for which the Cayley graph of DPS are all isospectral and not isomorphic. Okay? But this is not so difficult. To be honest, for groups like that, which are basically almost cyclic, you basically can compute the eigenvalues almost basically completely, and then you see that you can arrange that many of them are going to be the same. Let me make a remark just to show you, because sometimes one should separate here between the easy question and the difficult question. Let me just mention that once you have such examples, you can get many other Cayley graphs which are isospectral and not isomorphic. But frankly, they're not so interesting. Let me say it anyway. Corollary, you see, let's take such dihedral group and embed it into some group G in some way. Doesn't matter. Just assume this is, you can embed dp inside a huge symmetric group if you want. And now you have two set of generators of S1 and S2, which gives you here isospectral graph. Let's say that this is just A1, B1, and this is A2, B2. Okay? Now, now I claim that the Cayley graph of G with respect to the set G minus E A1, B1. So I take, it's kind of silly, I take as my set of generators all the elements of the group, except of these three elements, is isospectral, isospectral, not isomorphic, to the Cayley graph of G with respect to E, A2, B2. So if I throw away these three elements, they are isospectral, not isomorphic. Why? This is trivial. Because assume you take the Cayley graph of G with respect to the full G, except of the identity, you get the complete graph, right? This is the group. If you throw out these two generators, you get a complement. Okay, sorry. Look at the Cayley graph of dp with respect to A1 and B1. If you take the Cayley graph of G with respect to A1 of B1, they don't generate. That's fine. But they generate the H1, and then you get copies of H1 of this Cayley graph on the cosets. Right? Now, all these graphs are isospectral to each other and not isomorphic, and this is not connected graph. But this is the complement of this, and this is the complement of that in the complete graph, and then you can easily see that the complement of them are isospectral and not isomorphic. But of course, this is kind of a silly example, and because as I said, the real problem, like with expanders and in many other things that we are interested in eigenvalues of graph, that we are really care about bounded degree graphs. So besides of this and this little observation, to be honest, very little is in the literature. For example, here is an open problem which is so easy to state. Find two set of generators, A and B, in the symmetric group, Sn, with A equal to B bounded, with the Cayley graph, can we find in the symmetric group two set of generators which are, again, isospectral, not isomorphic. Even this is open. So you see, if we can use the symmetric group to take G to be the symmetric group and take all the elements except of three, then not possible. But the real question is, can we do it with a bounded number of generators? And this, we don't know. In a kind of a peculiar way, we managed to prove the following strange theorem. So we are kind of interested in simple group. I mean, the same question for A and for the alternating group, it doesn't matter. But we can prove the following. fix D and P, there exist two, in fact more than two, okay, let's say D greater equal 5 and say not 6 for some reason. There exists two sets of generators of size F. I can write you explicitly, but let me, depending on D on and P of, for every R, for every natural number R, we can find a set of size F, D, P of SLD P to the R. We take the field of order P to the R. We take this infinite field such that the Cayley graph of this S, maybe I'll write PSL, it doesn't matter. I just want to show you, here are finite simple, so we have an infinite family of finite simple group with two set of generators which are isospectral and not isomorphic. Okay? What? Oh, I'm sorry. Okay. What? Yeah. Okay. So here is an infinite, so like for every P and every D, we get an infinite family of finite simple groups, which with a Cayley graph isospectral and not isomorphic. Now, what? In a way, well, they depend on R, but the size of them does not depend on R.
So it should be AR.
Okay.
Set of generators.
Set of size, generators. Okay, AR, BR, okay, size this, or PSLR, such that. In a way, they don't depend on R. You know, it eventually will come up from an infinite group. You know that. We are going now to the infinite world. Right. Okay, so I kind of have to apologize from now on, because up to now, the question, now I have to use many elephants in order to kill a mice. You know, it's a kind of a down-to-earth problem about finite groups, but we are going to use quite a lot of infinite dimensional representations, etc., etc. So I will tell you basically the story. So the story really, or what made us to think about this problem, related to what I told you before about isospectrality of Riemann surfaces and the theorem of Allen-Reed. So basically, the theorem of Allen-Reed told us the following: that there are Riemann surfaces. You see, Riemann surfaces of genus G are always obtained like that. You take PSL2R, you divide it from the right by a maximal compact subgroup, which is SO2. Now, this is the famous upper half plane, the hyperbolic plane. You divide it from the other side by some gamma 1. Now, you get a Riemann surface, and that co-compact lattice, a torsion-free co-compact lattice, and that's the general form of a compact Riemann surface of genus G greater or equal to. To say that this is isospectral, now you can probably believe me that, okay, so maybe, sorry, this manifold is, now I'm not talking about isomorphism, now just isospectral at this point, isospectral to exactly the same thing, PSL2R divided by SO2, this is a maximal compact subgroup by gamma 2, this is really if and only if this is very similar. What? Yeah. This is very similar to this story. This is if and only if as G, now G is PSL2R representation, take it to here, L2 of G mod gamma 1 is isomorphic as a G representation to L2 of G mod gamma 2. Okay? So, even the language is the same. As this is the spectral decomposition of that is if and only if what in representation theory people call the spectral decomposition of these two representations. You see the group G acts from the right on G mod gamma 1. So it acts on L2. This is an infinite dimensional Hilbert space which is decomposed as a direct sum of infinitely many irreducible G representation. If this decomposition is the same as this composition, the two manifolds that are isospectral. And now, as I said before, there are many gamma 1 and gamma 2. There are this method of Sunada which can ensure us that we get this isospectrality, and also he showed that there are many cases in which they are not isomorphic. What?
What is the tool for showing non-isomorphism?
So in the Sunada case, his tool was the following. It took him what?
Yeah, in another case you explained.
I said, oh, okay, no. So this is, for this case, this is still an open problem. It's still a famous open problem. For some reason, John Thompson was very interested in that. But this is still, even talked here in Jerusalem a few years ago about this problem. And it's still an open problem. Are there Riemann surfaces which are isospectral and not even commensurable? Not isomorphic, but not even commensurable. This is still open. Really what we proved is the following theorem for D greater equal. Now, and Alan Reed proved that if gamma 1 and gamma 2 are arithmetic and isospectral, then they must be commensurable. Now, what we proved that if D is at least 3, there exists gamma 1, gamma 2 arithmetic in PSL dr such that the same thing but replaced with D. PSL dr we divided by a maximal compact subgroup SOD. So this is isospectral, not even commensurable, not just isomorphic, not even commensurable to exactly the same thing in D. Okay, this was our first interest. The technology that we implemented here, when one do it over a local field in characteristic P, enable us to get the discrete result. So let me basically explain the technology to do this, and then I will get back to the Cayley graph. And as I said, this is really the same kind of technology, but I'll have to throw in a lot of theory. The first theory is about the construction of arithmetic groups. How one?
I think you promised to tell us what arithmetic is.
Yeah, so that's. I'm not going to tell you exactly what it means because that will take the full hour. So I first of all I will do the usual trick which people do in colloquium, and when they have to explain what is an arithmetic lattice, they say something like SLNZ. But SLNZ, what? Yeah, I need two of them. Okay, no, but I basically will describe you what's the general, one of the technologies to get arithmetic lattices, the one which is used here. And unfortunately, it's not that trivial. Now, what you have to do, what you do to get, let's say, an arithmetic lattice in SLDR, you take a number field, which is some field actually, we can take even, yeah, I think I can take today even k equal q. That's not going to be my problem. Let's take even k equal q. And then you take a division algebra of degree d over q. So this means this is an algebra whose dimension is d square, but this over d, but every element over q is invertible. It's a division algebra, skew field. Now, there is a elaborate theory to classify all the possible division algebras of the over q, the so-called Brouwer group, which give them. And it's known, let's do it really over Q. I think I don't need really any extension. Such D division algebra over Q. Now, usually, for many, if you take a field extension of Q, then for many fields, for most fields, for almost all fields, if you take D and tensor it with an extension like with complex number always, but even with the real number, with the periodic numbers, what you get, it suddenly becomes D tensor F is equal to the matrices, so this if, that's not always the case, but it's in most cases. It's the D by D matrices over the field F. And then we say that D splits over F. Okay? And if it's not, if it's, there is also intermediate, but I don't want to talk about that. Let's just say that it's, and if it's still a division algebra over the extension, then it ramifies over F. Now, D is determined by the finite set T of primes, P, such that D tensor QP ramifies. Namely, does not split. It is still a division algebra. So this is kind of a rare situation. It happens finitely many times. And it's determined by this set of primes so that this ramifies, but plus some invariance, plus for every P in T, a number, we can think of it, a number in maybe the Z mod DZ, a number, let's call it A of P in Z mod DZ. So if somebody gives me the set of prime for which D ramifies and those number AP, I can recover the algebra. That's classical theory. At least here in Jerusalem, we used, or it has been used to be taught when Amitzur was around. Maybe nowadays it's less popular. A much more famous theorem is, look at the case D equal 2. This is AP here, which is not 0. In fact, it's even AP prime to D. Now take the case D equal 2. In D equal 2, we don't need this invariant, right? Because it must be 1. And that's a famous theorem that if you take D equal 2, then we are talking about the so-called quaternion algebras. And it's known the quaternion algebras over the rational number are completely determined by the set of prime for which they ramifies. This is only finitely many of them, and if I'll give you the list of them. If you go for d greater than 3, you need this plus the invariant. Now I will get an additional requirement. Assume also, and we can always arrange that. Assume that D tensor R does split. It's really that. And we can get, in fact, for every finite set of primes, you can arrange, and every set like that, so that the sum of them is 0, you can find. There are plenty of such division algebras. Assume you have this situation. Then you can, okay, I won't give you the, then somehow out of this D now, you can see that if I will look at D, I will look at the point, say the integral point of D and the invertible one, they will give you a discrete subgroup of SLDR. See, some of the rational points are now inside this. The invertible element are inside the D by D matrices. And if I take the integral point, I will get a lattice. And this is, an example of a construction of an arithmetic lattice. Okay? But now we're going to use another big tool, even bigger than this. And this is the so-called Jacquet-Langlands correspondence. Jacquet-Langlands correspondence somehow teaches us, gives you a map from, so let's call this lattice here, let's call it gamma D. So I start with subdivision algebra, and I'm getting a co-compact lattice in SLD. If D is equal to, I start with a quaternion algebra, and then I'm getting a co-compact lattice in SL2R, and this is the way to get an arithmetic Riemann surface. In Jacquet-Langlands correspondence, it's something very fancy. Usually it expressed in the adelic language, but as a consequence of it, you get the local Jacquet-Langlands correspondence, teaches us how to embed PGL, PSL, say, DR over gamma D. See, now I have this group, and I have this gamma D, right? I'm interested in understanding this representation. You remember, this representation is the representation which, if I find two different Ds with the same decomposition as a representation, they will give me two manifolds which are isospectral. What? Now this is still for every D. Now they embedded into some space which is, let me even skip. This is a big space which is independent of D, but this is just an embedding. Okay, I don't have time to explain. You need the language of Adele. But if you follow, but it gives you a description of what's the image of it. And the beautiful part is that the description of the image depends only on T and not on AP, on these numbers. Which means that if I start with two different division algebras with the same T but different AP, I'm getting two lattices which are isospectral. Good. Here you see the difference between d equal 2 and d larger than 2. If d is equal to, there is no meaning to this AP, because this AP, all of them are equal. So the t completely determine the gamma d, right? If d is bigger than 2, then I still have a little game to play with this AP and to get arithmetic lattices which are isospectral, and which are isospectral at least. Why they are not isomorphic? Well, here you can either, why they are not commensurable? It's a little bit more difficult. So you can either use some more algebra. Yeah, here you must use some more algebra. Okay, you have to do it. Let me skip it because I want to say a few words about the Cayley graph, which is the discrete object, which are our main interest. Okay? Now, but everything which I said so far is enough also, almost enough, to prove also this theorem. And it's kind of amazing that we are using such a huge machinery eventually to prove something very, very down to earth about Cayley graph. And you can really construct example like that and say, here are the two Cayley graphs, here are the generators. Everything is explicit. They are isospectral. They are too large in order to really check it by computer that they are isospectral. And definitely we cannot prove directly that they are not isomorphic. Okay, but now how we get Cayley graph? The story with Cayley graph is the following. And that's very related to the lecture of Ori Prajansevsky this morning. What we do, we take now, instead of working over the rational number and over the real numbers, we will take global field. So now we take K to be FP T. We take polynomials. Maybe I'll call it X, so that T is. We take polynomials, rational functions over the finite field of order P. All the theory, that's kind of general philosophy of mathematics. Whatever you do over Q, you want, you can. Sometimes it's easier, sometimes it's more difficult to do also over this global field of characteristic P. In particular, you can take division algebras, division algebra over this K, and this enables you to get co-compact lattices gamma D, co-compact discrete subgroup in PSLD over the local field FP double brackets. You see, if you take all the formal power series, the formal Lorentz series, in X, you're getting a local field, a locally compact field. We can talk about Lie groups of characteristic P, which is one of them. And we get a co-compact lattice. Now, this group now, if you divide it by a maximal compact group, you get the so-called B, the Brouhat-Titz building, which is what Ori talked about this morning, which is a D-1 dimensional contractible simplicial complex. So this is an infinite simplicial complex. This is an infinite simplicial complex that we get like that. Now we apply the same machinery. We take D with ramifications at the same primes, but with the different invariants as before, and we divide this by such gamma D1 and then by gamma D2 to get now quotients which are simplicial complexes, which are isospectral. Okay? By exactly the same Jacquet-Langlands and all the... How do we get Cayley graph? Oh, sorry. Which are isospectral. Now, to prove here that they are not isomorphic, not commensurable, we can do the same machinery, but there is a problem here. What we get? We get simplicial complexes. They are not isomorphic and not commensurable as simplicial complexes. But I want to prove that they are not isomorphic as graphs. Right? Because eventually I want to get non-isospectral graph. How do I know that they are not isomorphic of graph? So, well, building is something which is, I think, combinatorial people call it a Klee complex. Namely, the structure of the complex is completely determined by the one skeleton. So if two of them are isomorphic as graph, they must be isomorphic as complexes. Now let me warn you, as graphs, they are commensurable. There is this theorem of Layton. Every two graphs with the same cover are commensurable to each other as graphs. So they are commensurable as graphs. They are not commensurable as complexes, but they also cannot be isomorphic as graphs because of the clique. Or if one wants, one can use here maybe quicker Mosto rigidity theorem. Mosto rigidity theorem tells you that if the two objects are isomorphic, they must be conjugate, and this is impossible. Anyway, we can add that. In the last 4 minutes, I have to explain still how do I get Cayley graph. You know, I'm still in a very abstract world. And here is the last secret. Cartwright, Steiger. Cartwright and Steiger in 98 in the Israel Journal of Mathematics published a paper which so useful for us for so many applications, and I never understood why they did it 20 years ago. I once asked them and said because it was so beautiful. And indeed it's so beautiful. They found groups which acts discrete subgroups, arithmetic, so they are really of this form, which acts simply transitive on the building, on the vertices of the building. Now think about it, and if it's easier for you, think about a tree. Assume you have a group which acts simply transitive on an infinite tree. So what does it mean simply transitive? It acts transitive and there are no stabilizer. Namely, you fix an initial point, and for every point on the tree, there is a unique element in the group which takes you to that point. Which means that you can identify the vertices of the tree with the group. Moreover, if you take as your set of generators the elements we take the initial point to the immediate neighbors, you see that these are generators, and the tree is isomorphic to the Cayley graph of the group with respect to these generators. The same thing is for the building. So you can see, you can take such a building, you can take that group with the generators will be those elements which takes an initial point to the immediate neighbors. Okay. Now this is a number which depend only on D and P. Right? This will be a Cayley graph of an infinite groups, which acts. And in fact, the Ramanujan complexes that Ori talked about, at least some models of them, are obtained like that, exactly like that. One can write them very explicitly. Even in the original work of mine with Sarnak and Phillips, the fact that we have the so-called now LPS Ramanujan graph, the fact that they are Cayley graph is really what happens there. There is a group acting simply transitive on the tree. So now we have groups acting simply transitive on the buildings. Now, if you have a situation like that, now think about it. If you now replace this group by some congruent subgroup modulo M, modulo I, where I is some ideal, then you see what you get if you take a smaller group. If you divide by the full group, then it's like dividing the Cayley graph of the group by the action of the group. You get just 1 point. If you divide by a normal subgroup of finite index, you get the Cayley graph of the quotient. You see? So we have instead of doing it just for this, we do it with the same I here and here. There are infinitely many for every R. For every R in the theorem, we can get such an ideal I, such that what we get, that these quotients, even though they are so abstract, they are basically simplicial complexes built on Cayley graph of some well-chosen finite simple groups. And these are the finite simple groups that we got here in this theorem, and I'm exactly on time to finish. Sorry?
I remember this construction for D is 3. Do they do it also for any D?
Okay, oh, why? Okay, here, this is for every D. Okay, we have problems with D equal. Okay, what we need is really, it's really the issue of this AI. If D is 6, you remember, I have to choose them to be prime to D. Now, with D equal 3, there are only 2 elements, 1 and 2. With D equals 6, there are only 2 elements, 1 or 2. Now, the problem is that somehow, if you choose the 2 algebras with opposite signs, exactly opposite, they are still commensurable. So we leave this out, the 6 and 3. And 4 also. Basically, we don't have just 2 examples. We can do it phi of D, where this is the Euler function divided by 2. This is just checking what the... What?
The Cayley they can produce Cayley graph for every D.
Oh, yeah. They didn't produce this Cayley graph. They didn't talk about the finite quotient at all. They talk only about one infinite lattice, discrete group, acting simply transitive on the vertices of the building. They produce for every D and every P, and even for every Q, if you take... Yeah, and in more than one. You have now. What I want to say, much later, it was proved by Mohammadi and Alireza Saleh Goldsfidi that there are very few discrete subgroups like that acting simply transitive of the vertices in characteristic 0. Mumford found one example many years ago, which became very famous because of implication. Shai Evra, my student who is not here anymore, is now in Princeton, and Ori Prajasevsky recently found an infinite family in PGL3, but in characteristic 0, which are important for some application to quantum computation. There is a lot of things to say here, but the 2 Iranian, Mohammadi and Alireza, proved that if D is 8 and above or 9 and above, in characteristic 0 you cannot do it. So it's really, we are so lucky that there exists such lattices in characteristic P, and we made a lot of mileage on them somehow for various combinatorial down-to-earth applications. Yes, you can take even FQ, we're talking characteristic P.
No, in 0 characteristic, we know that if you take...
In 0, no, in 0 characteristic, even if you take a extension of p-adix, there is absolute bound on the dimension. Above it, you have no lattice acting simply transitive, or even transitive, I think, on the vertices of the building. Yeah, it's a somehow for some strained region, the behavior is very different. Yeah.
Beforehand, you mentioned the generators A and B, and you wanted to say AR and BR. So what you can think of is you can think of the trickster generators A and B in the original field, and then you're reducing them modulo different ideals. Right? That's to say the generators,
Yes.
in each case, they're being
Yeah.
one set of
Right, that's what I told Benji before. There is really an infinite group, and all of them are finite quotients of it, and I'm taking the generators. I have 2 different infinite groups. Both of them act simply transitive on the building. I take generators for this one, generator for this one, modulo ideal, they give isomorphic groups, but completely different generators. So. But the number of them is the degree of the building, which is fixed. It's a fixed number, and I can easily write to the formula what's the degree. That's well known.
Other questions? No, so let's thank Alex.
Thank you.